Alright, so welcome to the videos on the life cycle of stars. When you look up into the night sky, of course when you look up into the night sky around here it's not that impressive, but if you've ever had the luxury of being able to go out into dark areas, like in a national park or whatnot, when you look up into the night sky, you're bombarded with the beauty of multitudes of stars just everywhere. And while a photo like this is a long exposure, you wouldn't really see it to this extent. If you're in certain dark areas, you can actually see the Milky Way, the galaxy that we live in. Maybe you've wondered, where do all these stars come from? Ironically enough, it's the gaps in between the stars where uh, the birth material of stars comes from. This gap in between stars is called the interstellar medium. Basically, what exists between stars. Kind of like cities. Think of stars maybe as like cities, and all of the country in between the cities would be like the interstellar medium. What's different though is that it's there's not much of anything out there. The interstellar medium is so not dense that even artificial vacuums that we make on Earth, a vacuum being uh, where we try to suck as much material out of a space as possible, so there's basically nothing in there. Um, the vacuums of space are better than any vacuums we could possibly make here on Earth, for the most part. So, what exists between stars? Well, basically, it's gas and dust. Gas being atoms and small molecules, and most of the gas is the atom hydrogen. And dust are bigger clumps of material, dust-like particles, soot-like particles, things like that. Um, and you can see here, this is a nice nebula, a nice cloud of gas. And here, actually, the gas cloud blocks the light from the stars behind it. You can see some of them trying to peek through. They look a little bit redder here. And of course, we got our Milky Way galaxy, and you can see it's bright, 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 but then there's this sort of dark band right here. And that is actually a large, vast array of dust and gas blocking the light from the stars behind it. So it exists. Um, and as I was mentioning before, it's not dense at all. The average density of gas in the interstellar medium is about 1 particle per cubic centimeter. So this is not to scale, but if you take a centimeter by a centimeter by a centimeter, there'll only be 1 particle in there. And that may not be shocking to you until you realize that if you take 1 cubic centimeter of the air that you're breathing, there's literally billions, if not trillions, of air molecules in there. So this is insanely not dense. Dust is quite a bit less dense actually, and it looks confusing based on the drawings I have here. Um, but if you look at the scale, this actually is a 1 kilometer cube versus 1 centimeter. There's 1,000 meters in a kilometer and 100 centimeters in a meter. So each side is actually 100,000 centimeters here. And in that cube, so if, you've all traveled a mile before, and um, a kilometer is not that much smaller than a mile. It's a pretty long distance. So if you have a cube with a kilometer by kilometer by kilometer, it's only about 1,000 dust particles in there, out in space. That's basically nothing. You could go hundreds of feet before hitting the next particle. That's crazy. In terms of the gas, like I said, the interstellar medium is mostly made up of hydrogen. Then there's some helium, and then some heavier elements. Uh, it's thought that hydrogen was the primary, since it's the smallest and the simplest element. It was the primary element in abundance after the universe formed. In terms of dust, we're not still very sure exactly what the main composition is. We can obviously look at the light coming from dust and see, what it's made up of, but um, in order to get a good survey of that throughout the universe, that's not something we've really done yet. So, gravity is always trying to clump material together. That's the force of gravity is an attractive force, and it pulls mass together. And this force of gravity even works on the interstellar medium, gas and dust particles. And as gravity pulls these particles closer together, they form these nice cloud-like objects we call nebula. Now, this is again, this picture is covering a vast area. If you were in space here, you would not it would not look like you're in a cloud. This is still not. This is still very, very, very not dense. I don't know if there's a better way to put that. Um, but the only way you can really see a cloud of this nature is to be really far away and be able to take in a wide area. Because again, a cloud on Earth is billions probably times more dense than this cloud. And again, like I said before, gravity is always trying to clump materials together. Um, so then why don't all these clouds just immediately collapse down if gravity's always pulling them together? And of course, the universe is pretty old, so there's plenty of time to pull them together. Well, there's two different competing mechanisms going on. There's gravity pulling in and heat kind of creating an outward pressure. If you've ever boiled something, you know that the pressure increases, like a pressure cooker, for example. The pressure increases because the particles, as they heat up, they move faster. And as they move faster, they are able to exert a larger outward pressure against if they're in a container, they're banging on the inside of the container harder because they're moving faster. There's not really a container per se in space, so what the end result is it just expands out. And so there's a balancing. You got, based on the temperature, it'll expand out a certain amount. You can think of actually the container as gravity, and gravity pulling in. And so based on a temperature, it'll only go out so far until the force of gravity pulling in equals that outward sort of pressure. And that's where you create an equilibrium. In order to go in more, to overcome gravity more, you have to heat up more. Okay? So, I'm sorry, you have to get more mass in order to go in more. To go out more, you have to heat up more. So that's the red arrow here. So, how do you get to the point where you could actually turn a cloud like this into a star? You just keep getting more and more mass. The more mass you have, the stronger the force of gravity acting on all of these particles, and it will go in more. Of course, doing that heats it up more, and so you're going to really keep getting more and more mass. So you need huge, huge, vast nebula clouds in order to start making a star. Um, Even then, sometimes it's thought that gravity isn't enough to get a massive nebula to start collapsing into a star. Sometimes it's thought that a jump start is needed, and um, a jump start is really just some sort of pressure. Ironically, one of these forms of pressure can come from the death of another older star or a supernova. So a star explodes near a cloud, near a nebula like this one, and that pressure from the supernova will squeeze the cloud in this area, and then gravity's like, hey, thank you, I'll take that and extra energy and just start collapsing more, and new stars are formed. This is a picture of a galaxy. You can see this is the arms of the galaxy. Let me use a little arrow here. There's a little arm of the galaxy here, and an arm of the galaxy here. And this is where star formation is happening. You can see all the clouds, all the nebula. These sort of reddish areas. There's probably a lot of stars, older red stars in there too. But there's stars in here that are dying, and as they explode, they'll compress the gas and dust near them, and new stars will form. When we talk about galaxies, we're going to discuss that mechanism more. So you have a nice big cloud, and something gets it collapsing, and then it'll collapse into smaller clouds. And typically, stars form in batches. From one big cloud, you'll get multiple stars, and so it collapses down. This will split up, kind of like almost like cell division in a sense. And this process right here can take a couple million years to happen. On the grand scheme of things, it's a pretty quick event. So yeah, the individual fragment continues to collapse, becomes more dense, eventually causing the temperature to increase. As you squeeze, if you've taken chemistry, there's the gas laws and the pressure law, whatever, and as you squeeze material closer together, the temperature will rise. And as temperature rises, it's finally able to compete against gravity. So that's this whole balance of outward pressure from heat and inward pressure of gravity. And the collapsing stops. And you get to like this point here, and that can take a few thousand years to happen. So this is kind of where the birth of a star truly starts happening. And if you want to look at it from the point of view of one star, then we can ignore all the other ones and say, all right, here's our star we're going to focus on. Let's see what happens from here. And so here was the original cloud, and now we've gone down to this thing right here. And this is about the size of a solar system. So if you want to think of the life cycle of a star like our sun, then let's say this is the early stages of our star. This would be about the size of our solar system. So what's going on is finally there's some differentiation. So in the middle here, gravity has caused the density to be high enough that finally light can't easily escape. And if light can't escape, if that energy stored in the light can't get out, then it's stuck in there, and that causes it to really heat up in there, and it's starting to get hot, starting to look like there's a star in here. Meanwhile, out here it's still pretty cool, but there's still a lot of material that can continue to condense into the star maybe, or start to form the other parts of the solar system like planets and things like that. And so we're going to stop there and then start talking about these later stages in the next video.